Hi, my name is Atticus Tiplady, and this is Project 1.3, a counting circuit. Firstly, let's talk about the button input. The button input is a way to demonstrate what pull-up and pull-down resistors are and how they affect a circuit. In this circuit, the circuit starts off with one of the output/LEDs remaining on as there is current flowing through it, while one of the output/LEDs remain off as there is no current flowing through it. The first circuit will remain on as it relies on a pull-up resistor. This current is able to travel through the 10 kilo ohm resistor as there is an open path. Once a circuit has flown through the resistor, there's a possible junction point where it can split. The other circuit, on the other hand, relies on a pull-down resistor, as when the button is not pressed, there's no current flowing through it. The circuit relies on the momentary PBNO, as without it, the circuit is closed. Once this button is pressed, the current will flow and split at the junction point. Part of the current will reach and pass through the output, while the other part of it will travel through the second 10 kilo ohm resistor. Next, let's talk about the NAND gate oscillator. The NAND gate oscillator is arguably the most important factor of the circuit. RC1 and RC2 apply a lot of intel on how the circuit works, while the NAND logic gate does the majority of the work. The NAND logic gate is a chip in which, if there are no positive charges on both sides, the output will be positive. Here's a truth table for the NAND logic gate. There's not a lot going on in the circuit as there's 4 NAND logic gates. Each of these 4 NAND logic gates play a huge role in the circuit, but RC1 and RC2 play the main role. RC1 in the circuit affects the duration of the LEDs. This means that when the button is not pressed, the LEDs will stay flickering for a while. RC2, on the other hand, affects the frequency of the flashes. When RC1 is supplied a lower capacitor, the LEDs will stay on for a shorter period of time. When we sub out the capacitor for a smaller capacitor in RC2, the flashes will appear more frequently. If we were to connect something such as the 417 decade counter, we could get it to start counting the flashes that the NAND gate oscillator is emitting. Thirdly, let's talk about the decade counter. The decade counter is another add-on to the NAND gate oscillator in which it utilizes a 417 decade counter IC to count the flashes that the NAND gate oscillator is emitting by connecting the wire from the NAND gate oscillator to the decade counter. This way, the decade counter starts to count how many flashes there are. As we see here, the circuit is counting how many flashes are coming through by applying them to a bar graph. This is possible due to the pin configurations on the 417. Now, moving on to the decimal up-down counter. The purpose of the circuit is to demonstrate how circuits can count in binary number systems by incorporating 4510 IC and 4 LEDs. Instead of counting in decimal, the 45 counts in binary code. The 4510 adds a bunch of new things to its pin configurations like the up-down pin and the reset pin. What this circuit is doing right here is it's counting in binary, where each of the LEDs represents a different value. For every spot you move in binary, you multiply by 2, starting at 1. So 0001 would be 1, and 0010 would be 2. Section E and F sort of fade into each other as Section E sets up for Section F, which is the 7-segment display. The 7-segment display utilizes a 4511 and a 7-segment display component for it to be able to work properly. What the 4511 does is it decodes binary into decimal, allowing us to create numbers as high as you would like by connecting more 4510s and 4511s, just what I've done here. The 7-segment display is a counter that can count from numbers 0 to 9. Every circuit that we have used was leading up to this. The 4511 pin configurations are also quite different compared to others. As you can see here, these are the pin configurations for the 4511. The 7 outputs on the 4511 connect quite easily to the 7-segment display as each of the outputs go into its corresponding pin with one common ground. If you would like to activate the decimal point, all you need to do is add a resistor coming from voltage. When connecting a 7-segment display to a circuit, it is important that resistors are incorporated. 7-segment displays are condensed LEDs with either a common voltage pin or a common ground pin. Due to this, the 7-segment displays need to have a resistor to prevent the component from drawing too much voltage and blowing up the LEDs. Thank you for taking the time to watch my video on Project 1.3, the counting circuit.